Welcome to another one of these. You remember our conversation for the last two videos, right? We've been talking about the journey of Voyager 2. August 20th, 1977, Voyager 2 blasts off from the surface of the Earth and has traveled through interstellar space to where it is currently 15 billion kilometers or more past the Earth. And what we did is we tried to estimate the amount of work in a very, very simple model that it would take to move from the surface of the Earth to infinity and beyond, as a matter of fact. This led to what we call an improper integral, the integral from 1 to infinity of k divided by x squared. Now, an integral is improper for one of two reasons. The first reason is that one of the bounds, 1 or infinity in this case, is infinite. And of course, the upper bound is the infinite one. The other possibility for an improper integral is that the function that we have in the integrand, k over x squared in this case, is discontinuous for some point in the domain. For either of those reasons, we might call a definite integral improper. Well, we also looked at a whole class of improper definite integrals, right? 1 over x to the p. P was equal to 2 in the case of the Voyager 2, but p could be 1/2, p could be 4, p could be 3, p could be a lot of values. And so what we found was that if p was strictly greater than 1, then the improper integral from 1 to infinity converged. If p was less than or equal to 1, then we came to the conclusion that in fact the improper integral diverged. Now, today we're coming across this very unfortunate circumstance, and it's this. Rarely are our functions as nice and simple as 1 divided by x to the p. They're usually more complicated, right? So, in fact, today we're going to wrestle with the example, the improper integral from 1 to infinity of 2 plus sine x divided by x squared. And if we look at this, we see that this is, at least the denominator, is suspiciously similar to the denominator of k over x squared. Of course, the difference is we don't have a constant k in the numerator for the example that we're going to deal with. We have this function 2 plus sine x. So what do? So here's the big picture for the comparison test. What we're going to do is we're going to take a function whose integral we don't know if it converges or not, and compare it to a function whose integral we do know if it converges or not. So for example, you might think that 2 plus sine x over x squared, it might be reasonable to compare that to 1 over x squared, and then check the integral convergence of each of those. And that's exactly what we're about to do. So let's do that. If we look at 2 plus sine x, we can take advantage of the fact that sine is always in between -1 and 1. Since that's the case, then we know that 2 plus sine x has to be less than or equal to 2 plus 1. And we have an x squared on the bottom. And 2 plus sine x must be bigger than or equal to 2 plus -1 over x squared. If we rewrite this, then of course we get 1 over x squared less than or equal to 2 plus sine x over x squared less than or equal to 3 over x squared. In other words, we're starting to get functions that look an awful lot like things that might be used in our p-test. And in fact, what I'm going to do is I'm going to focus in on 3 over x squared and try to make a comparison of the convergence of it with relationship to 2 plus sine x over x squared. I think a visual interpretation of what we're about to do would probably be very helpful. So let's go ahead and take a look at the graphs of 3 over x squared and 2 plus sine x over x squared. The first thing that we observed is that 3 plus x squared is greater than or equal to 2 plus sine x over x squared at all points except for a couple of spots right here. Now, if we start to think about the convergence of an improper integral, one way to think about that is we can think about the area underneath 3 over x squared. So if we take a picture of that, look at that, the area underneath this integral, underneath this curve is really the improper integral 3 times 1 to infinity 1 over x squared dx. And by the p-test, we happen to know that this thing, in fact, converges because p is equal to 2. In other words, the area is finite. Well, let's think about the area underneath the 2 plus sine x over x squared function. It can be characterized by the improper integral that you see in front of you. And in fact, at least visually, it's pretty obvious, right? The area underneath the blue curve has to be less than or equal to the area underneath the red curve. And so we can write that down mathematically with our improper integral notation. But we can take one step beyond that. We know, in fact, that this improper integral right here, the integral of 3 over x squared from 1 to infinity, converges and it's finite. Well, this 2 plus sine x over x squared happens to be bigger than or equal to 0 in all instances. And in fact, if we integrate from 1 to infinity, this turns into 0. So what we have is we have an improper integral that is bounded below by 0 and bounded above by a finite value, and therefore it must converge itself. So by comparison, we are saying that compared to something that we already know, 3 over x squared, we know how it converges. We can therefore conclude that 2 plus sine x over x squared also converges. Okay, let's do another quick example to see if we have a good idea of what's going on. Let's look at 2 plus sine x over x to the first power now. We can do the same thing we did before. We can drill in on the function itself and point out that it's got to be less than or equal to 2 plus 1 over x and bigger than or equal to 2 plus negative 1 over x. In other words, 1 over x is the lower bound of this function, and 3 over x is the upper bound of 2 plus sine x over x. So this time, let's focus in on 1 over x and compare it and the convergence of that function to the convergence of 2 plus sine x over x as we take the improper integral. Well, again, let's look at the area underneath 1 over x. It's characterized by this improper integral. Again, by the p-test, p is equal to 1. This implies divergence. And since 1 over x is always non-negative from 1 to infinity, that in effect means that we have an infinite amount of area underneath the blue curve here. Well, if we look at this and we look at the area under 2 plus sine x over x, clearly we can articulate that area by this improper integral, and it's got to be greater than the area from 1 to infinity of 1 over x. So we write down mathematically what this means, what this says. So if we have an infinite amount of area here, and we have an area that must be bigger than infinity, that means it has to be infinity itself. So that means we, in essence, the improper integral of 2 plus sine x over x diverges. Okay, this leads us to what's going on, to a statement that we can make about the comparison test in general. So in general, you got two functions, f and g. F is going to be the larger function always over our domain. G is below that. We're always going to assume that g is going to be non-negative, 0 or greater in other words. And additionally, these two functions, f and g, are nice. That means that they are always continuous on the domain that we care about. So our comparison test says this. If the integral of f, the upper curve converges, then the area underneath the lower curve must also converge as well. The second statement comes from our second example. If the area underneath the lower curve diverges, it's got to be infinite, then the area underneath the upper curve f also must diverge. But we have two other cases really. Case number 3 says that if the area under the upper curve diverges, when we look at the area under the lower curve, we don't really know what goes on here. It may diverge, it may converge, it may be finite, it may be infinite. All we know is that it's less than or equal to something that is infinite ultimately. So we can draw no conclusions. And the fourth possibility is if the area underneath the lower curve converges, we don't really know what happens with the area underneath the upper curve. And the reason for this is it could be finite, it could be infinite. We don't really know, so we draw no conclusions. And we have to use some other approach to make the determination of convergence. Okay, where are we at? The convergence test says that if we have two nice functions. And nice means they're continuous over our domain. It also means that f is greater than or equal to g, and g is greater than or equal to 0. If we have those two scenarios, then we can draw two possible conclusions from that. And then two conclusions which we don't really know what's going on. So, you know what to do at this point. We got some prep problems for you. Go ahead, do them, and we'll see you next time.